next week is the first London event-driven meetup. So this whole thing about event-driven architecture, which I think a lot of you are aware of, it's like Gartner just talked about it as one of the top 10 trends in architecture and technology. So that's a big part of what this is about. One thing that's changed for me personally since the last meetup is I'm now the CEO of a company called EventStore, which is an event a stream database built from the ground up for event sourcing technology, originally created by Greg Young, and actually this guy was one of the co-inventors, co-founders of EventStore. So that's one aspect of event-driven architecture as a whole. But this is not about EventStore. This meetup's not about EventStore. It's about event-driven architecture as a whole. So if anybody, we're always looking for people to sponsor, to speak, and get involved in any way. We want to grow the Seattle community. One of my goals, this is part of why I wanted Rob involved, is to have Seattle become one of the leaders. I live in Seattle, and become one of the leaders in this space, in event-driven architecture. And with what we've got from a cloud-based perspective and some of the leadership from Nordstrom and others, it's something I'd really like to grow in the Seattle area.
Yeah, I just want to mention we have a little stamp card, and if you go to the London, Boston, Seattle meeting, you get a free beer. Yeah. It's a little ledger, and you immutably stamp it 4 times.
Exactly.
It's not geocache.
And we have Chris Condren, who's the CTO at EventStore out here. James is co-founder and chief architect at EventStore. And we have Adam Dymitruk, who's down from Vancouver, who's going to be speaking tonight on event modeling. And Adam's from AdaptTech. He's the CEO at AdaptTech Group. I use the AdaptTech Group. And he's going to be speaking on event modeling, which this is a preview of a book he's already writing. I think we might even get to see the cover of the book, maybe. We'll see if he actually gets his presentation up and running. So Adam's going to talk about event modeling, and then James is going to speak today about the Raft consensus algorithm and some intersection with events and event-driven architecture. So, all right, welcome. And take it away, James.
Okay. So originally this talk was supposed to be second. So firstly, it's quite short because originally I was going to be what was between everybody and the work, and now Adam gets that distinction instead. So he can talk faster. The second thing is it's quite code heavy, and this projector is charitably garbage. So it's going to be kind of interesting to see how big we can zoom things and how we can text wrap to make this actually work. Maybe. We'll see how it goes. If at any point there's something that you can't see and you would like to be able to see, then please just interrupt. Or if there's any questions, then also please just interrupt. It's a small enough group that that's not going to be a problem. So what I was going to talk about was the problem of distributed consensus and one particular approach to solving it. And once upon a time I had a bunch of really nice slides done that demonstrated the problem, and then someone did this instead, which is all animated and stuff, so I decided I'd just use this instead because it's much friendlier. So the problem with distributed consensus is an interesting one. It's been... Thank you. Perfect. It's an interesting topic that's been the subject of research since probably the late 70s, I guess, and various papers that have been published on it over time. So the root of the problem is, okay, let's assume that we have a computer that's trying to store some value. Right? If we have a single node, it could be a database storing one value, and we have a client that's trying to store that value, then coming to agreement about what that value should be is really easy if we have one client and one server. Right? The client can send the value to the server can store it, and the server can reply and say, okay, that's the value that's stored. So the problem is, what happens if we've got more than one node? So say we want a fault-tolerant cluster so that we can lose one if the power goes out or if the network partitions or something like that. How do we get all of these servers to agree on what that value is? It turns out this is a somewhat hard problem, and it's the problem of distributed consensus. So getting a bunch of machines to agree on a particular value. So there's been a bunch of research about this. one of the first, not the first, but one of the first popular papers about this was the Paxos paper by someone who's now at Microsoft Research called Leslie Lamport. It's kind of an interesting paper to go read, and I recommend people go read it once they've understood more about other problems first. It's one of these papers where it talks about this island, or like this, I think it's a single island, a Greek island somewhere, and the governmental model of it, and rambles on about a bunch of different stuff, and at the end says, oh, by the way, you can use this to solve distributed consensus. And everyone's like, surely this can't be the answer. So there's a second paper that the same guy published, Leslie Lamport, and the abstract of that is, apparently it's too difficult to understand the first paper because everybody's an idiot, so here's a simpler version. And it turns out that actually that's not much simpler either, because Paxos is just a hard algorithm to prove. It was one of the first that was actually like theoretically proven through so that every branch can be proved that it will come to the correct answer. It's also really hard to implement. Has anybody here tried implementing Paxos? Has anybody had fun doing that? Cool. Is anybody's... Okay, yeah, I mean, fair enough, it's fun. Is anybody's implementation of it in production? Okay. So I've done it once, and it's in production, and it's the kind of thing that once you get it working, you just don't touch it again because you don't want to like risk breaking it somehow. So eventually there was, hold on, who was it? Diego on Ruff paper. So eventually someone did a PhD paper which was deliberately designed to be understandable. So this was a way of looking at this problem from Diego Ongaro that was deliberately designed to be able to go through and understand from first principles actually how this thing works and to be able to reason about how you should go and implement it in actual real-world conditions. And actually, it's a very understandable paper. It's been revised a couple of times. This extended version is the one to go read. But actually, so this got published in 2013, maybe? Okay, so this one was published in 2014. I think the original was published in 2013. And since then, this has sort of become the preeminent consensus model that people are using in production systems just because it's actually reasonable to understand. So I think Cloud Spanner uses Paxos sort of proper, and various bits of Azure, I believe, also use Paxos. But many of the newer sort of cloud native systems are using Ruffed underneath them. So etcd, which is underneath Kubernetes, HashiCorp's Consul and Nomad, both use the library that we're going to talk about tonight. And it's become sort of a fairly popular, hard but not impossible project for CS students as well. And so what I'm going to try and do is walk through a little bit about how this algorithm works with that animation again, and then try and map that into something a bit more practical than just abstract theory. So the HashiCorp library for this is a fairly commonly used one. There are two commonly used libraries for this in Go, at least. One is the HashiCorp library, and the other one is the etcd library. So the HashiCorp library is inside Consul, Nomad, probably some other things. I forget exactly. The etcd one is inside a lot more things, but it's a lot, actually, I think, more complex to understand. That's inside CockroachDB, etcd. There's a big list of users on the etcd Ruffed implementation. But so what I'm going to go through and do is build out that simple one-value database server that agrees between nodes what the value should be using this library, and walk through the actual usage of the library rather than the implementation of it itself. And then if you're interested in more, I recommend going through the code for the library in conjunction with reading the paper. So the code for what I'm going to do, on the basis that it's kind of hard to see, is available on my GitHub. I'll put the URI out later. But it's fairly straightforward to go read. And if you want a sort of a clearer, sort of slightly less blurry version, I've done this talk before. So that might be a sort of an easier way of doing it. Okay, so if we go back to where were we? Here. So the fundamental thing that most of these consensus systems have is the idea of a strong leader. So the way we're going to decide which node gets to decide what the value is going to be is by having an election and voting one of the nodes to be the leader,
and then that will decide what the value is, and that will replicate out its values to all the followers. So that's the terminology that Ruffed uses for this, leaders and followers. And each one of these servers is a node. So the first thing we need to do is work out, well, how are we going to start an election? So the way that works is, okay. So any node can be in one of three states. It can either be a follower, in which case it's going to receive values from a leader somewhere. It can be a candidate, so there is, it doesn't think there's a leader right now, so it's going to try and start an election. Or it can be in the leader state, in which case it's going to allow proposing values to the followers. So when we first start an application, every node is going to become a follower. And every node is going to have a random timeout on it that says, if you haven't heard from a leader in X period of time, then you're going to become a candidate instead. So every node has a different timeout so that they don't all become a candidate at once, and then you end up with elections that no one can win because everybody's trying to start elections at the same time. There's probably some kind of lesson in this for, they should just have an electoral college instead, right? That improves everything. Maybe I won't go. Yeah, that's not funny. Yeah, I agree. You can have the Russian nodes over here interfering.
I think that's called Chaos Monkey.
Right, exactly.
5 nodes for that?
Right. So within the timeout that each node has, if it hasn't heard from a leader, then it becomes a candidate. And what a candidate does is send a message to every other node saying, hey, vote for me. And then it votes for itself, and it waits to hear back, to get votes back from a majority of other nodes. So if you have a 3-node cluster, you have to get voted for by at least one other node. You can vote for yourself, and at that point, you've become the leader. So nodes reply. If we've got a majority, then we become the leader. So we're denoted with this sort of thicker ring. So that's how we determine where a leader how a leader should emerge. So what happens for a second if, okay, that's not what I wanted to do. Okay, let's talk for a second about how this can fail. So let's imagine for a second that we have a network partition that separates all 3 servers from each other. So of course that never happens with local networks, right? Sure. Also never happens in AWS, happens every 5 minutes as far as I can tell. But if none of these servers can talk to each other, then whoever's the current leader won't be able to hear, or the followers actually, they won't be able to talk to each other. So at some point within that timeout, they'll start a new election, and they'll vote for themselves. And in the pathological case where no node can talk to any other node, then what will happen is each node will vote for itself, try and request votes from other nodes, but they won't be able to receive that request, or they certainly won't be able to receive a response. You can have lopsided network partitions where you can talk one direction but not the other, particularly fun. So in that case, you can't sort of get a leader. If none of the nodes can talk to each other, then no one can receive enough votes to become the leader. So assuming the algorithm's implemented correctly at each node, and that's a big assumption, but if it's implemented correctly at each node, then you can't have a leader unless you've got a majority of nodes able to talk to each other. So what happens if you've got a network partition that just separates one of the nodes? Right, we know we're in a 3-node cluster, so this one could start an election, vote for itself, request a vote from this one up here, which can reply, and then we have a majority of nodes. So can anyone see why it might be a really bad idea to run this with 4 nodes? Sure. So you have a network partition down the middle, and each one can request 2 votes, and if each one can vote for itself and talk to one other node, then you end up with a split brain, right? You end up with 2 leaders, and effectively the system completely diverges. So whenever you see these kinds of systems, they tend to be run in odd numbers. So you either run 3, in which case you need a majority of 2 to win, or you run 5, in which case you need a majority of 3. If you run 4, then actually what you really end up with is still needing a majority of 3. So actually you just have less fault tolerance and more overhead. But it is possible. Okay, so how do values get set? So assuming we have the client, so assuming we have our leader and we have 2 followers and we have no network partition, so everybody can talk to everybody, then the aim of having a leader is that every value change goes through the leader. Right? So the client can send a value to the leader, and it will make a log entry suggesting what the intent of this action is. So in this case, we're going to say we're going to set the value to 5 because we only have one value. And then we keep a log of that, similar to a write-ahead log from a relational database or something. But what we don't do is update the value that will be read back. So if you were to go and read the value from the leader right now, you would see no value because we've never set one. And this value of 5 is not committed yet because it's not replicated and acknowledged by a cluster. So at this point, what we have to do is replicate out the intent to all of the other nodes in the system. So all of the followers, we could multicast it, or we could send it over a unary transport to each one. But somehow, each of the followers has to get that value. And when they've got the value, they can reply saying, this is an acknowledgement. And when we have a majority of nodes that have written the entry, we can commit the value. So the first place we commit it is on the leader. So at that point, if we were to go and read a value from the leader, we would see this 5. But if we did it at this precise moment, actually if we went and read from one of the followers, we would not see the latest value, we'd still see the uncommitted one. So we've committed it, and then we can notify the followers that the entry's been committed. This is kind of like similar to the 2-phase commit kind of model. And the followers can update their value as well. And suddenly we've come to consensus. So this is kind of a common system that, actually this isn't that different to what something like Kafka does for writing log streams. I guess most of the competitors have a similar kind of model underneath them for replication. Certainly EventStore does. Sadly, EventStore's replication was written in 2011, before Ruffed was published, so we do the same thing with a more complicated election system because we don't want to touch it because it works. So so leader election. Okay, so we've got these couple of settings that can control this. Let's assume we have our nodes here for a second, so we've got A, B, and C. The first timeout that we need to talk about for controlling these is the one that determines, am I going to be a candidate for election? Right? So am I a legitimate follower right now, and I've heard from the leader within this timeout window, or do I need to start an election? So we randomize that to be between, the some number of milliseconds that depends on the network environment you're in, the round trip time, that kind of thing. And that's a trade-off between false positives for slow messages causing new elections and the time to recover it in the case of an actual legitimate failure. So when the first node here to reach its election timeout becomes a candidate, starts a new election, and then it increases this thing called a term which is the kind of the election number that we're on throughout the lifetime of this system. So we start off and we haven't had a term yet, so we start off by incrementing it and we have term 1. And this is a way of disambiguating which election process we're talking about at a particular time so that you don't end up with people voting in the wrong election. I'm sure there's some kind of joke to be made about that as well. But, okay, so when you request a vote from another node, one of the things that's included on the request to vote for you is the term in which, the election number in which you're going to vote. And as soon as you get one of those requests, as soon as you request from other nodes that they're going to vote for you, you reset your election timeout so you don't immediately start another election. But you start counting down in case you need to become a candidate again. Okay, so we already talked about that. But the The other timeout that you need to control this is the heartbeat timeout. So this is, okay, so if I'm a, if I'm a follower, then how long am I going to wait before having heard from somebody to become a candidate? Sorry. So, okay, so we have the election that's the term that's currently in force, and we expect to hear back from the leader as a follower. Once we are in the follower state and we have a leader, we expect to hear from that leader every so often. And that particular window of time that we expect to hear from the leader from is called our heartbeat timeout. So in a busy system, you can carry heartbeats by data being written into the system. But on quiet systems, actually you can't do that. So you have to send explicit heartbeat messages in addition to the data going across the network, across the system. So that's kind of a, there's a bunch of edge cases for this that we can cause re-elections. We can end up where we have uncommitted data on a leader, and then we elect somebody new. There's a whole bunch of edge conditions with this, and they're covered really well in the paper. So what I'm going to try and do is try to put this into a more practical setting at this point and go over to some code. So basically what we have is what we're effectively doing is mutating a state machine using commands which are being replicated between each of the nodes. Right? And if we apply the same state machine on each node, we'll end up with the same result at each node. So in this particular case, we're using a really simple state machine of set this value. Right? We go into the state where we have a particular value, and that's the only transition that we can do. You can do much more complex things with this. And replicated state machines are a whole other topic, but we're just going to stick with our simple one-liner. One operation thing. So this little project here is an example building out that single one-value store using the HashiCorp Ruffed library as the underlay for it. So one of the first things we're going to have to do is model what the state machine that we're going to be mutating is. So what's the value we're storing in the node? And there's a little interface that you have to implement for this. And what you have to be able to do to satisfy that is apply a particular Ruffed log entry, which is a command like set the value to 5 or increment the value by 1. You have to be able to snapshot. So you have to be able to say, given us a state machine that's had a bunch of commands run on it, we want to be able to snapshot the value so that we can save it away to non-volatile storage and recover from it later. So if we were just keeping track of one value, a snapshot is going to be a single integer, basically. If you're in a more complex system that's mutating, say, a whole key value store, you might have to snapshot out the entire state of a key value store, or a map or something like that. And the other thing you have to be able to do is, from your snapshot, you have to be able to recover the state of the state machine at the point in time the snapshot was taken. So all we're really doing here is storing a single integer. So we have a state value on this finite state machine struct, which is, is there anyone that has never seen Go before and can sort of understand what's going on? Or?
I can get what's going on.
Cool. Okay. So we have, this is going to be, we're going to have an instance of this struct that's actually going to be the finite state machine on our node. We're going to have a state value, and we're going to protect it by a mutex. Not strictly necessary here because integer changes should be atomic, but if we had two values, for example, we'd want to protect them with a mutex so that we don't get a torn read of half the update and half not. Okay. So when snapshotting is easy, right? We only have one value. So all we're going to do is write this thing out as, this snapshot is a type built into the library. You just give it a value here, and it will deal with storing it on disk or in memory or whatever, depending on which implementation you give it. But in this case, all we need to do is copy out our value. And when we restore it, we happen to know that the snapshot is encoded as JSON, which is kind of an implementation detail. that we don't control. So we can decode the snapshot as JSON and then take the value from the snapshot and put it back into the state machine to restore the state of it.
James,
Yeah.
Is the apply ordered, and the reason that you need the mutex is because the snapshot might happen at the same time? Is that
So the apply is ordered. So if we had, if we set the value to 5, then set the value to 6, then set the value to 7, then set the value to 8, then it's guaranteed that those applications will be done in the same order on every node in the system.
And it'll wait for them to finish.
And it will wait for them to finish.
Applies to the next one.
Right, indeed. The reason we need the mutex actually is not for application and snapshotting, because it won't snapshot concurrently with apply. The reason we actually don't need the mutex in this particular case. The reason we would need it, let's say we had state value 2 here, and our commands, rather than just affecting one number, affected 2. So it was set A to 5 and B to 6. The reason we need the mutex there is that you can go and read the value of the state machine at any point in time, right? So what you could do is say, well, we've set A to 5, but we haven't set B yet. You could go and read the state machine at that point in time, and you get a torn read in effect.
I see. So it's just for servicing reads at the same time.
Exactly. So the library itself guarantees that you won't snapshot at the same time as you're applying a log entry. You could also take the mutex if you wanted to be super safe there, in case implementation details ever change. But, okay. So how do we apply these log entries? So the snapshot and restore is kind of straightforward in this case. We're just saving out the number, restoring the number back into the state machine. But the real question is, how do we update the state machine? So this log type is the thing that gets replicated around the cluster. So the leader sends out these log entries, they get taken into a queue and then applied in order to the state machine on that node when the value gets committed. So one of the things that's in there is this sort of opaque data holder, which is just a byte array. And in this particular example, I've chosen to serialize it as JSON just because it's really easy. So we're going to use this type here, event, to represent the commands in our log. And the commands are going to have a type and a value. And in this case, we actually only have one command, so the command type is set. So when we get a log entry from our queue, we can go and deserialize the JSON, or unmarshal the JSON, I guess, if you're in Go. And at that point, we'll have an instance of our event struct up there, and we'll be able to say, well, what does this command tell us to do? In this case, it's set, because that's the only thing it can tell us to do, and it will have all of the required data on here. So in this case, we set the value, because our commands were of the form set x or set y, where x or y was the value we want to store in our database. So in this case, we're about to go and modify the state machine instance. So we need to go take this mutex. Again, this is unnecessary for this one example, but if you were going to modify 2 fields, you'd really want this. And then we can just go and change our value here. So we can guarantee that these things are going to come through in order, in the order that they were committed to the leader. They'll appear on the followers, and they'll get applied at the point at which they get committed. Okay, so that's the FSM side of things. That's actually the majority of the example. Right? We don't have to do very much to use this library. But one of the things that we're going to need if we want to be able to demo this thing is we're going to need some kind of way of reading and writing from our Ruffed cluster. So the way we've done that is just with a little HTTP server here. It's a bit more complicated than it needs to be because it logs a bunch of stuff. But we handle posts and gets, and if we post a value, then we write into the leader of our Ruffed cluster. So what we do to do that is, remember our little event struct? We go and build one of those to go and stick on the command queue. We marshal it as JSON, sort of as the opposite end of the application process. And then we can call into the Ruffed cluster. So regardless of which node you're on, the library will actually forward requests. The library is capable of knowing if you're a member of a cluster right now, it knows who the leader is, sort of by definition. It knows if it has a leader, and if it has a leader, then it knows where the leader is. So it can forward requests to you. That's particularly useful because otherwise you end up with clients connecting and disconnecting from a particular host every time the leadership changes. And that can cause, if you're in a small system, it's not a problem. If you're in a big system, it can cause all kinds of problems with sort of thundering herds of clients going around a system as the leadership changes. So this server is the root of our program here, but node, the Ruffed node is the route into the Ruffed library for our particular use case here. And we can just say apply these events with a timeout of 5 seconds. So if we haven't come back in 5 seconds, then we have some kind of problem here. You can tune that value according to some things that are described in the README, which I can't remember offhand. 5 seconds is quite long. So eventually we're going to get a future value back of this, and if we've managed to commit this value to the if we don't manage to commit this value because we've timed out, then so a reason we could time out here is, okay, we don't actually have a leader right now. We're trying to commit a value, and the cluster's in a state where there's an election happening, and let's say we're in a network partition, so actually we can't have a leader elected. So none of the 3 nodes can talk to each other, so it's impossible to get a leader elected. In that case, we're going to time out after 5 seconds and stop trying. In the usual case where you can talk to a majority, then that's never going to be hit. So that value is kind of a trade-off between how long you want to wait in the case of failure versus false positives for failures. So assuming we apply successfully, we just write back to the client saying, OK. If not, we write back saying, internal server error. So that's how we handle posts on our HTTP server. For gets, we just read the state machine value. And actually, what we should do there is, here is a bug. And although it is a bug, it's not a bug that will actually have any effect on this value, on this particular thing, because we're not. I'm kind of surprised. A lot of people have seen this, and no one's ever pointed that out before. So, yeah. Okay, so to read, we go and take our lock. We go and construct a value by reading from our particular node's state machine. So that gives us the committed value at that particular time, which, bear in mind, might be different between the leader and the followers within the time period it takes to commit to a follower. And then we just reply over HTTP. So there's a bunch of other little bits that we have to do for housekeeping. One of the things that we have to be able to do is handle nodes joining a cluster. And we also choose to handle that over HTTP right now. Most of this is boilerplate that you can just copy-paste from the documentation. So the actual Wireup for this thing is fairly straightforward. We have a bunch of configuration, and we start the Ruffed library going on its own, sort of on a background thread, a background Go routine in this case, which doesn't really map cleanly onto an operating system thread. If you're on like a C++ library, it will probably just run on its own event loop on its own thread. Basically, we try and post a join to whatever the address of our cluster is, and start this thing going in the background, and then just leave it running in the background. We also start our HTTP server and leave it running. The interesting part is actually in constructing the Ruffed node. So one of the things that we have to do, every server in this model has an ID, which can be used to determine that you don't have 2 votes from the same person, or that you don't try and join 2 nodes from different clusters together. There's a bunch of different transports you can use. In this case, we're using TCP because we're going cross-process. If you want to test things using this library, there's also an in-memory transport, which runs exactly the same way, but everything just runs over Go channels instead of network connections. We need a Ruffed Logstore. So it's kind of important that if we've stored a bunch of values that have been committed but haven't been applied yet, that have been replicated but not applied yet, that if we need to restart for any reason, that those values aren't lost. So we have to have some kind of persistent storage for them. There's a bunch of different implementations of this that come with the library. This one uses BulkDB because it doesn't involve compiling C. There's also ones for LMDB and for like Badger and a whole bunch of other key value stores, sort of local key value stores. We can also use the same thing for snapshot storage and for stable storage, which is the committed entries. Eventually, there's just a bunch of Wireup that we have to do here. But the key thing is we designate one node as the Bootstrapper. So the Bootstrapper is responsible for waiting. This is a library-specific thing. It's not part of the protocol, but it's a practical implementation detail. Eventually, what you're going to do when you start a cluster for the first time, you're going to start one node first with a flag that's something like -- bootstrap, and then the number of nodes to expect. And then it's going to wait for join requests from all of the other nodes up until it has that number that you told it should have, and then it will start the election process. So what this prevents is you having to hard code in where all the nodes are coming from ahead of time. And it also prevents you not knowing up front how big your cluster is going to be. Because if you don't know how big your cluster is going to be, you assume you have a cluster size of 1 in effect, and then you have to deal with cluster membership changes. So it's much cleaner to just wait until you have all of the nodes that you expect and then start everything, rather than have like an election which you win because you're the only node, and then you get a second one join and have to reconfigure everything.
James, it seemed to me that the join protocol was implemented by the caller of the library. Is that right? So so the library has a callback for joining, and you can implement that however you like. Okay. So in this case, we're just sending a JSON over HTTP request because that's what we implemented as our server. You can implement it using whatever you like. Okay. So you actually had server code that was the join?
Yes, exactly. So actually the server code was in this HTTP. We had a handle join. So in the request, we expect a header, which is the peer address, which is who's making this request, and then we can add the voter to our particular rough node. So one of the other features of this library, which is part of the extended version of the paper, and I believe not part of the original published version, is the idea of non-voting nodes. Someone had fun with the naming of this. So in the HashiCorp library, you have nodes with and without suffrage, which is as good a way of describing it as I can think of. It is, yeah.
I wonder who that someone was.
It wasn't me, just to be clear. It was, actually, I know who it was. It was James Phillips, who now works at Netflix. So the piece that implements that, we're going to receive the request, and we're going to call this add voter as a result of that. So you could implement this over any transport you like. It's just that HTTP is nice and simple for this case, so that's what I did. So there's a bunch of Wireup. There's a bunch of configuration that you need because in general these nodes have some important when it comes down to it, the config points they need are what's the network address that we're going to run the Ruffed protocol over? What's the network address that we're going to serve HTTP for clients and join requests over? Which node do we want to go and join? So we're going to start one with the bootstrap flag and all the others with the join flag. And the join nodes are going to go talk to the bootstrapping one to get started. What path do we want to store our data at? And are we bootstrapping or are we joining? Has anybody ever tried configuring console? Does this look familiar? There's like the way you bootstrap a console cluster. You start one node with bootstrap expect, and you start all the others with join. Yeah, it's not an accident. It's just because it's exposing this library to get consensus before it runs. So there's a bunch of code here to handle dealing with config. Does anybody write Go primarily or for projects? A little bit. Okay. So there's one library that I really wish everybody would use everywhere, and it's not the Ruffed library. the one that I wish everybody would use is this one called GoSockAdder. And what that allows you to do is specify templates for network addresses, and it will resolve the template at runtime. So one of the template options you can have is you could specify like the bind address to be a template like get private IP, and it will find a particular private IP for the machine. So that's one in the RFC 19 whatever it is range. But you can also pipe these, so you could get like I think you can do get addresses. This is paraphrased, but you can pipeline these things into the smallest. This is not the name of it, but this is the principle of it. Smallest mask, and then take the. I'll just find the documentation. It'll be easier. Yeah, so you can do all these kind of things. So you can say like, okay, find the node that's that has a default route attached to it, so that you can talk to the internet through this one. The reason to do this is so that when you go build cloud images, you don't have to hard code IP addresses in or run scripts at startup, because it will just go and work out the correct thing to bind to, and that saves everybody from everything binding to 0000 / whatever. So that's a really useful library aside from this. But most of the config code here is just, it's parsing values from the command line and putting it into a config struct. Okay, so what does this look like if we run it? This is going to be interesting because there is not much space on this projector and there's quite a lot of text to fit on it. Let's see if we can, actually, let's do this differently. Let's see if we can split each of these two ways. This is interesting. Okay. So there's a little helper script in the repo to go run this code. All that does is takes a node number and converts it into a bunch of different ports. So we say we're going to run because I'm running all on localhost, I have to choose different ports for each of the Ruffed nodes. So what we say is that for the node number, I can make this a bit bigger. For the node number, we're going to start from 7,000, so do 7,000, 7001, 7002. For the HTTP port, we're going to do 8,000, 8001, 8002, and store the data in node X. And then we're going to say, if we're node number 1, we're going to bootstrap, and if not, we're going to join node 8000, which is the first one. So this is just a cheat for constructing the correct command line arguments for these. And then it just calls the program with that particular string of arguments. Okay, so if we run the first one, I'll run it here and then minimize it out the way for a second. So run node 1. Okay, so the log's going to be kind of hard to see here. But we can see actually already some of the concepts that we've talked about here. So the election timeout was reached. So we have a new election. We need 2 votes because we've said we're in a 3-node cluster. We're in term 23 now, but that's because I already have data on this. Actually, it would be more interesting to start from scratch. So because I already had data, this cluster actually already has data in it, and it's had a leader before. And the term is consistent over the life of the cluster, not just the time this program's running. So if I be very careful about this. Sure, why not? Okay, cool. So now if I run node 1, okay. So we see we reach the heartbeat timeout. We enter the candidate state in term 2. We need 1 vote right now. We actually never told it how many nodes to expect, so this is going to expect 1 node, and we're going to deal with cluster resizing as we join more. So we need 1 vote. We voted for ourselves, and we won the election, so now we're the leader. Cool. That sounds... Yeah, I was going to say, there are some states that work this way, I think. So let's go start node 2. Okay, I can... this is going to be kind of harder to see, I guess. Maybe I can zoom it a bit. Okay. So what happened here? Okay, well, we entered the follower state as... we joined a cluster which has a leader, and the way we deal with that is we just become a follower, and we increase the quorum to the next n+1. So now if we terminate all of these, both of these, and go restart them again. Oh, where did that go? So we terminate both the leader and the follower. So we terminated 1 and 2, and go and start 2. Then we're in the situation now where we know we need 2 votes, and we're not going to get them because only one node is running. So if we go run node 1, we should be able to get a stable, we should see an election, and we should see a stable interesting. Okay. Huh. Okay, so it joined this time. So you can see we started 1 and then 2 joined it. I'm not sure why that didn't work the other way around. I think it's to do with the bootstrap flag being set still. That's something you only want when you actually start up the first time, and then you're supposed to take off. So, okay, so we started 1. It was waiting for an election. We joined 2. So you can see we got a request to /join. We replied with 200 to it. And we should see if we look in here that we are a follower somewhere here. Okay, maybe our logging isn't going quite as we expect. Okay, so we can join a third node. We should see okay, so we're entering a follower state, and we have, so I think something's particularly screwed up here, and I don't know what it is. But, of course. And I didn't change the code. I also didn't recompile the code. No, the Mutex isn't the problem here. Sadly, I wish I could blame it on the Mutex change, but I didn't actually recompile it, so it's not that. And I think we have a stable cluster at this point. I think. So we have 1, 2, and 3 in order. So let's just terminate what I think is the leader and see what happens. Okay, so we terminated the leader, and okay, so a couple of things are happening here. So 2, if we find, we go back here, we got a new election happen, and we needed 2 votes to win it. So we voted for ourselves, and number 3 voted for us also. So we won the election, and we became the leader. So number 2 is now the leader. Number 3 is the follower. That's good. Apparently I screwed up the logging and didn't actually print the leader. But what's interesting is that this, the current leader is also still trying to talk to the dead node. So if we went and restarted it, it should just become a follower, and then a bunch of stuff will happen. It will try and start an election. It will fail to start an election because there's already a stable cluster, and it will join. Okay, so we can get a stable leader, kind of, if we screw around with it enough. So does the HTTP interface work? And that is...
How are we doing timing-wise?
We're quite a bit over. Sorry.
I want to make sure we have time for questions.
Uh-oh. Okay. Okay, well, if there are questions, then feel free to ask them while I'm doing this bit, and then I'll try and answer them as I'm going, and then hopefully it will work at the end of it. But what I'm going to have to do is go look up what the path to the HTTP server is, because I completely forgot it.
So I have a question for you.
Sure.
In most of the cloud service providers, they do this for you transparently within a region,
/key.
within multiple availability zones. So for
Sure.
example, AWS, DynamoDB, or S3, you have a 3-root replication, and they're managing leader election for you. It's transparent to you.
So I wouldn't assume that's the case. I believe that DynamoDB is actually leaderless.
Oh, okay.
It's not a consensus-driven thing. The Dynamo papers I'm not an expert on the implementation of DynamoDB, but I don't believe it has a leader.
Okay. So if you wanted to do,
I think it uses quorum reads actually. So,
okay.
but maybe Adrian knows more about that actually.
Got
He's
it.
as a resident Dynamo expert, not DynamoDB, but Dynamo paper expert who works on Cassandra, DynamoDB is leaderless, right?
DynamoDB.
So the Dynamo paper is designed isn't a consensus system. It does quorum reads and quorum writes in effect. Yeah. So I believe DynamoDB is the same, and actually it doesn't do this, but other services do. So.
So if you have a in-region distributed system, whether it's quorum-based or leader election-based, and then you want to go multi-region,
Mhm.
are you familiar with anyone who is doing multi-region raft? So kind of a
So you can do multi-region Ruffed. If you have a strong leader across regions, then everything's just slower because you have the round trip time between regions.
yes.
What's more normal is to use something like console does. There's a particular diagram that I'm looking for, and they've probably moved it. Of course, I now get pictures of embassies. Actually, that's the one. So what a lot of people do is have a Ruffed group per data center, and then separate out WAN replication from LAN replication, and make that eventually consistent.
Right.
But you can run Ruffed over the internet just as easily as you can run it over a local network. You just need bigger timeouts because messages are going to be slower, and every operation is going to take longer. But there's no way of getting around that if you want the strong consistency guarantees cross-region, because you take a minimum of the round trip time to the to the two least slow regions. And if you lose, if you're a long way behind on another one, then your recovery time can be quite bad because you have to stream all the missing data over to the slowest region before it can become a follower that's voting.
So I believe that NetCD has some documentation on this where they have done that and they've figured out optimum timeout values and things. So they're experimenting with that and found like what doesn't work.
Right.
I know that they,
What doesn't work? Do they have what does work?
I don't know. I think they ended up with the same kind of thing like, hey, you really shouldn't do it. The timeouts get really funky and you can have really bad problems. So have two separate leaders.
Yeah, two
But-
separate.
But they did say
So you shouldn't ever end up with two.
why and how and what to do with timeouts if you wanted to do it, but it's not really recommended.
Okay, I'm not going to get this to the point easily where I can get it to work. I promise you it did work once, and I promise you the library works because it's running everywhere in console.
So I had a question, James.
Sure.
When you gave me the homework assignment to write a raft,
Yeah.
and I struggled with it. But one of the things I noticed was how similar it was to event store. A lot of the concepts in the higher level event store. You have commands, you have apply, you
Yep.
have events, you have
So if you're doing event sourcing,
sourcing.
then every object in your system is effectively a replicated state machine. So it is effectively something that you're taking a command and applying it to a particular state machine, and then, in our case, it's events rather than commands. But you apply these things in particular order, and you come up with a deterministic output for what the state is, and you can replicate that, and then it's the same thing basically. So yeah, it's not an accident, because event sourcing effectively reduces object state to being a replicated state machine, which is nice for lots of reasons. One of the reasons is you get all this research that you can use for it. So yeah, that's true.
So does this library automatically detect leaving?
Node leaving, it has calls that you can use for that. So in the same way as you can call add voter here, you can call so you can call demote voter, which will make it a sort of remove suffrage from an existing quorum member and reduce it to an observer. You can deregister an observer, and that will remove it from the cluster. There's also remove peer, which you can either do to yourself or to someone else.
But these commands are called by any node in the
So-
or there is a controller node?
There's no controller node as such. You can remove another node by making a request to the quorum. In general, if a node goes down, you don't want to remove it. What you want to do is wait for it to restart unless you know it's not coming back. And if you know it's not coming back, let's say because it was a member of an auto-scaling group and terminating it makes it go away forever, then you want to force leave it. So one of the dangers of this model before it had this feature was, so I used to come across this. I used to work at HashiCorp partly on console. And one of the things that we used to get all the time was people saying, I want to run console servers in an AWS auto-scaling group so that when one dies, a new one comes up. And what people would do is register so that it would join, a new one would join as it came up. But what happens is you join more and more nodes. So okay, so you lose one, you've got your 3 nodes running, you lose one, you start a new one. Right? So the new one registers itself, and as soon as the new one has registered itself, the majority needed has just become 3 instead of 2. Okay, that's fine. You can do that. What happens when the second one dies? Cool. So suddenly you only have 2 running servers. The other 2 are never coming back. And you go join a new one, and then you get 3. So you end up with a much extended period of downtime while a new node is coming into existence. Okay, so cool. So now you've got 3. So then what happens when that happens again? Suddenly you increase your majority again and again and again and again, and eventually you run to the point where it's actually impossible, based on the auto-scaling group constraints, to form a cluster at all because you don't, your majority keeps going up, and the number of servers is always constant, or constant minus 1. So that's the reason that forced leaving even exists in the first place, so to be able to reconcile the state of the world with what servers are actually going to be there. It's a lot more of a problem for clouds than it is or for dynamic infrastructure than it is for a static bunch of servers where you know the IP and you know where they're going to kind of come back from and to. Does that kind of answer the question?
Okay, so we need to move on. So
Cool.
Adam you have 10 minutes. No, I'm kidding. So let's take 10.
Yeah, okay. If anybody has more questions about that or whatever, then please feel free to ask. Thanks. And sorry about running over for so long.
Yeah, I didn't mention anybody who's interested. We're going to go to the pub after this. So James and I'm sure Adam will be there. Additional questions?
Let's see if this one works.
Again, I don't know. I think it's just the projector's got a weird, like it's super low.
I think, yeah, it's really low res. I had to change it to 720p.
Oh, is that what you did? And maybe
that's what I did, but it was...
Okay, so it's this damn thing.
But,
yeah, can you bring your laptop?
oh, yeah.
Oh, sorry, you have it here, right.
Let me mute it first.
Okay. Unmuted. Okay. So is that a countdown?
Yeah.
Oh, brutal.
and I had it as
No
well.
pressure.
Completely ignored.
No pressure.
James is really good at just ignoring.
Yeah, no problem. I got
Actually, I did that last time.
okay. How's the sound? It's all good? Okay. Let's wait for Dave. Okay. Okay, and in the interest of time, I'll shorten my presentation a little bit. So my name's Adam, and I just want to talk a little bit about event-driven as a concept and the fact that as human beings, we are more event-driven than we think. In the software sphere, we've been kind of forced to go down a certain avenue for building information systems because the constraints that were within this world, what we could fit on the silicon chip and what we could fit on magnetic tape and other magnetic media. In the 1950s and 60s, we made a trade-off to get accuracy and get speed because humans were not really good at that. We had manual processes where humans made mistakes, and humans were also at that point not very fast at doing those manual tasks. However, we did have very large filing cabinets. But the mistakes and the speed were not something that was a negotiable for business. And so as soon as insurance companies and other larger companies were able to afford computers and the storage, they made the trade-off. In those days, the storage was really expensive, really expensive compared to what a filing cabinet cost. So we were forced to deal with storage that was like this. And when we automated our businesses, we couldn't put what was in the filing cabinets into that space, or at least it was prohibitively expensive. As computing evolved, we had larger and larger amounts of space to use, but the patterns stuck. And what we had was a current state of the system view, and only that. Sure, we added logs, and we certainly looked at backups and maybe log printouts to find mistakes if they happened, but it was after the thought. It was certainly not the way businesses worked beforehand. When you go to your doctor and you have a visit, they don't throw away previous information and replace it with a new report. They add to a stack of all your visits, and there you can recognize patterns if you're getting cancer or something based on what the doctor observed. That's also in accounting, that's done in trading, that's done in a lot of places where we need that ability to go and check as to what happened, if there were mistakes or if we need more or different views in the future. That was the way business was done. Computing added this sort of constraint, and I don't think we really realize how much it affected how we build systems today. And this artificial view that we needed to have in order to take advantage of automation stayed with us. It stayed with us in the patterns that RDBMS systems provide. All the good parts of third normal form and being able to store an address only once instead of multiple times, those are concepts that were considered very important in terms of data integrity and started taking on a life of their own in each instance. So the interesting part about that is it's not really natural for a human being. When we discuss building these systems, we're forced to talk about static models if we're looking at how RDBMS systems are built and how we look at state. So what we really need to do is look at how our brains work and how we communicate outside of computer systems, and that's in regular systems. And when we communicate, whether we're selling something or we're talking about what something should do, as human beings, we're naturally gifted at telling stories. In fact, it's how civilization started. And event-driven has this awesome parallelism, is that if we use event-driven approaches, we tap into that innate human capacity to remember better and to communicate better. So how can we use that paradigm if we're going to use events to now build systems? And that's what my talk's about. I wanted to cover this kind of basic high-level look at history that I usually give a longer presentation on, but I just wanted you to sort of know where this kind of thinking suddenly dawned on me as I was introduced to event-driven from a technical perspective, but I see a lot more of a human side to it in terms of specifications and all these other aspects that are very human that really help us into running our systems and running our organizations. So I came up with a concept called event modeling, which is loosely coupled in a few previous works by Greg Young and Alberto Brandolini. So what Greg Young did in 2007, 2008 in Vancouver was really start a process of introducing event sourcing, so getting a stream of events to be the source of truth for a state of a system. That ended up being something that slowly made its way into also articulating the way an entire system would work and how subsystems would communicate within a larger systems. And these got terms like sagas or workflows and other things. So there's a lot of that greater sort of journey mapping, if you will, if you want to use some other concepts from UX or UI and those disciplines. And then later making it less of a whiteboard exercise, but more of a workshop exercise. And that's Alberto Brandolini's contribution to what I came up with in event modeling. And that's using sticky notes and having a very collaborative workshop. So he took that to a very human kind of interaction where you want to have participation from everyone in an organization that represents a number of different roles, if you will, or interests, such as anything from UI and UX to the CEO and the business vision to customer service representatives to salespeople that need to sell the product you're going to build. It really pays to have a common understanding of all those things. So there's this workshop called Event Storming that Alberto does, where people do this discovery workshop in terms of what the problem space is. However, it kind of leaves things like, go ahead and just do some other things like domain-driven design to implement that. And there's really very little guidance into how the solution or a particular try at a solution is going to look at. The difference between Alberto and Greg's approaches on the fundamental level are problem space, solution space. The Greg Young model really looks at exercising a bunch of solution spaces rapidly in order to discover the problem space, whereas Alberto is more about making sure we understand the problem space. And then we're kind of going to focus that as a technical aspect to actually implement. So the reason that I side with Greg's approach is because I find that all information systems really are these systems that have input and output. And if you really dissect what input and output is, it is the CQRS that Greg talks about quite a lot. If you dissect the fact that systems change over time, you notice that there's an event sourcing aspect. Now, because going back to what I said about the limited storage before, we throw away the historic events. But that doesn't change the fact that information systems behave this way and have a set of changes that happen over time. So all systems are CKRS, ES, if you want to use those complicated terms. They have input, output, and they have a ledger of what happened. And so why not use that paradigm to talk about them instead of having something else? So after 10 years of doing this, I actually have an opposite view of what I used to have, that it's actually more natural to do it this way. And so hopefully I'll show you how that is. So this is the only thing that you need for any information system. You don't need any fuchsia-colored stickies from Alberto. You don't need any user stories from your UX people. You certainly don't need any number of UML diagrams from activity diagrams. There's a whole lot of things that become redundant because we're going to investigate, sorry. Oh, great. Okay. Yeah, anyway, so let me remember the Homer Simpson dream in one of the episodes. All you need is this device. Let me show you. In this dream, and he wakes up, but he never gets to see the device that is going to make him a millionaire. So yeah, this awesome system, that's all you need. Anyway, for those Simpsons fans, you know the episode. After 10 years, I've distilled it to about 4 patterns for specification, and the format of the workshops and conversations that you need to have and how to collaborate with all those different roles. Because we'll take a look at how these things are exemplified in this simple, what looks like a very simple system. But we'll see that there's some interesting caveats to this, how some of the more complex things that you know from the industry are represented with a few simple 4 sort of common elements that we have on the right side: UI, API, or a job, command, read model, and event. There's a lot to talk about here. One of the key differences in specifying systems like this is it kind of takes into account of what we took as waterfall and misrepresented what waterfall was anyway, as we talked about earlier today, and swung all the way to being agile because that totally didn't work. But agile is also a very extreme point of view in terms of neglecting system design. And system design is a complex way of saying, how do we organize our information? And information systems aren't very technical, actually. We're not doing anything complex. What we're doing is we're managing information. We're moving it from left to right, yet we go to computer science classes in university to do that. It doesn't make sense. So there's a lot of overcomplication that has happened. And I believe that if we can find a way to communicate about what we want to do with a system, it's not actually a technical problem, and we can use various simple terms to communicate with that. The other thing that I've found is that for the first time, I actually believe in estimates again. I find that having a good plan and coming up to a blueprint that people can sort of see as the goal of what the system's going to do and how it's going to act, and it's not a technical thing. We know when we're done specific pieces, and we can start with the important ones. And because we have a better plan, we know that when we are done, we are done. And this is kind of the trick that Agile kind of played on us, and I've discovered this many years after, is that the emergent design aspect of test-driven development, for example, is at odds with itself. TDD is supposed to be something that gives you really solid code, right? You're supposed to refactor as you go so that you get all the solid principles in place. One of the solid principles is open-close principle. So how do you do open-close principle when you're forced to refactor the previous features you implemented? Doesn't that kind of strike anyone as odd? And how you can attain those 2 goals at the same time? It's a paradox. And one of the reasons that the estimates are all over the place is because through this refactoring, even good teams noticed that the 5th feature that they implemented was a lot faster to do than the 50th. Simply when you're implementing the 50th feature, you're refactoring quite a bit of logic, right? And that's not a technical concern, really. That's even a a business concern, because there you're basically redoing your entire business. And in Agile, we kind of force ourselves to be a little bit blind to the upcoming features in our backlog or what we have, so that we could concentrate on refactoring what we're building and making sure we're building on a solid. Do you guys get what I'm saying? It's kind of like you're trying to build on a solid foundation, but you're really building on sand because you're forcing that refactoring. So for the first time, these vertical sort of slices of this workflow that we can say is our blueprint of our application can be said that they're going to be done and we don't have to refactor them. That's a huge win, because for now, for once, we can actually empirically look at how long things are going to take. And we can take any number of these slices and have them predictably done in a certain amount of time, and especially a certain amount of cost. And that's very powerful, because the industry has given up with that. There's a no estimates movement and all this kind of stuff. And it's really moved information systems and all of the things that are software away from being engineering, when they really came from engineering practices. So this is kind of a shift back to making it more of an engineering thing. Now, you might think it takes a long time to do this. Some of these things take an afternoon to do for a project. It's incredible how fast you can get to replace what with a traditional waterfall, very sort of red tape process would take, many months into, a week or less, which is crazy that it would actually happen. But I've been there years ago, and after trying all these different things over the number of decades, this is the one that kind of got distilled. And while we have other approaches, I find that I can't simplify further than this, but I'm hoping to. We'll see how that's done. So the other thing about fixed cost is that you can farm out the work to who needs to do the work, and you can ask them to take on the risk of not delivering. In other words, you don't get to work on another piece of the system until you have finished, and any bugs that come back, you have to fix. So if you're going to make really crappy work, you don't get to work on future slices, and you don't get to bill for those. And that can be incentivized differently in a regular organization. But I'm looking at subcontracting a lot of the work, and a lot of people, I don't have the time to interview and give them like 3 months to evaluate them. So I need to give them a fair way to contribute and to have that contract to hire to find out if they're good enough, but at the same time pay them for their work. So how is that done honestly, right? This gives you an idea that I can say I can pay $5 or $50 or whatever per slice, and then if they finish 10 of them, they get paid that much. Because during that time, they were also incentivized not to have to come back and fix things if they got bugs. So that's worked really well. So let's dissect what this thing is and how you attempt to use it, because it has a lot of views from different perspectives, like I said, from sales, from UX, UI people, from designers, from testers, from developers. So one of the first things you'll notice is that we want to innovate, and we want to enable companies to be able to specify what they're dreaming of and test it with the rest of the people in the organization if it makes sense, or if they want to build that, or if they have other things they want to contribute. And so, James, I think I need a power. I think power just died. I'm going to pause the clock.
Yep.
So this is the third and last, I promise, technical difficulty tonight. Where's the plug?
Down there.
Here.
I guarantee you can't guess his password.
I just hope it turns on. So this is the third and last laptop I'm attempting tonight.
It's coming back. I have backlight at least. Come on. Actually, you know what? Let's unplug this for a second. Oh, no, it's not working.
Anyway, I'll continue talking so that we just don't, while this pops up. So that last diagram, imagine you're still looking at it. is something that was missing from Alberto's approach and Greg's approach, was the idea that you can talk about the UX and the UI parts of a system when you're designing a system. We always concentrated on the state of the system and what events flowed through it, and all those sticky notes that we talked about was concepts and things that we kind of were writing a book about what's going on. Thanks, James. This little part up here, the UI part, was always missing with DDD, with any number of things we had. So I know you can't see it really well. I'm just graying out the rest of the diagram. So as I go left and right on these slides, you'll notice that all that you change is what I want you to concentrate on. And the reason I'm doing this is just to show you that the different perspectives on the same diagram speak to very different concepts that are very important to different groups of people in an organization. And through that, you now don't have a proliferation of documents that certain people have a specialization in, and then you have to wait and throw things over the wall to a different department. We're trying to find a common way to communicate together throughout an organization, no matter what your job is. In this instance, we're using this diagram to communicate with the UX, UI people, the product owners, to describe what it is that we're building. The top part is what was missing, that UI part. What the customer does, what the administrator does. You can divide that into rows. That's your UX. Down below, we have the events, the things that the system remembers. Someone signed up, someone purchased a book, someone added something to their cart. Whatever system we're doing, we can show the narrative, and you notice that this has a very good resemblance to what you see in the movies as a storyboard and storyboarding. You have key frames as to what's happening. So visually you see what's going on, you understand the plot underneath, and you see how everything intertwines. And that makes for a really good platform to communicate all the user experience points. You can include non-technical things as events over here, as someone actually walking into a store, or whatever it is. But you can communicate across what is going on. And give it a separate swim lane if you want, if it's not a technical thing that you're going to implement, or maybe it's something you bought off the shelf that's going to do that for you. That's fine. But you understand what's going on at this point. And notice also how the legend changes as I move from slide to slide, what things are involved. Because we only have those 4 pieces that we're doing. You get 4 Lego blocks.
So, Adam, could you read the bottom? It's hard to see it because of the...
It's great. It's not meant to be you can read it now. Right? Yeah. Okay. All right. So does everyone see how the innovate portion of starting a project at a company or being a startup, how this can be used to start that? And essentially, that's, usually with event modeling, what you do is you start the brainstorming process and you come up with all of these orange stickies that you brainstorm about. Oh, what else can we do? Can we buy a product? Can we add something to the cart? Do we get a notification, an email? What else happens? We can put all those down as things that happen, and then we put them down on the line, showing them making sense in a specific order. And we can discuss why something can't happen before another thing. And we can discuss that a few previous things must happen before this one's allowed to happen. We can talk about the story, right? From there, we can engage with the UX, UI people to say, can you just quickly take that marker or go on the whiteboard and draw those wireframes of how you think that UI is supposed to look on that app and what they're going to see in that email at this point, right? So we can collaborate together to get the whole picture. Secure. After we're done, this is looking at the end. We look at the very beginning. Let's go at the very end once your system's complete. I can block out everything else and I can look at the paths for all the data. And I can look at where things cross boundaries, where we have credit card data coming into the system, where it's getting stored, where it's living, where it's getting pulled out. We can see all those pathways. And this is something that a security person would love in any other architectural diagram. And they have to tease it out of most organizations. They have to have interviews with this department, and this team and that team. And this team had their documentation done this way, and that team had it done that way. So when you have a complete picture of where information flows to on a timeline, so they can say when it happened, your security audit is easy, or at least an order of magnitude easier. So a company that I work with, they can do the regular job in a fifth the time, and they still charge the same amount because the product from their security audit is superior to any others. So It's a triple win, right? Which is pretty good. So back to actually building the system. So the meat of it is the middle, is building it. And every information system, or every system in fact, has two things. And this is the input-output, CQRS, read command side, but also it can be divided into things about what you do for a user. And one of them is you empower the user. That means when I change the state of the system, I know that when I arrive at the hotel in 2 months, I'm going to have a place to sleep. So I've been empowered to change the system to benefit me, right? And we do that by allowing a command to be accepted. We say, book that room. And that room booking is just an event. Room booked with all the particulars about that particular event. And that's it. We can specify it by giving a regular given when then, or arranged act assert, or if you're from the UX, UI perspective, you're a designer, you're probably looking at the same parallel, and I just can't believe this hasn't been really made more obvious. Situation, motivation, and value. Has anyone heard of that from, I think Chris has probably he's here from Vancouver from Plenty of Fish. Really the largest dating site, and they have a really awesome UX UI department. And they're, as any other organization, sitting in a separate place, not playing with everyone else to do that. And that's not their fault. It's just that we haven't realized these common ways of interacting, like having this common place to interact with those people. And so we have highlighted here the command. And this is what James was talking about. It's like, okay, great. Well, how does Plenty of Fish make sure that we can make a command work across 7 million, concurrent online users? James told you how that's done. But from the business perspective and from everyone else, we still need to know that we're doing this and we're changing the system, and that we can specify whether that command succeeds or not. And that's how we do it. The other part that's quite important here is that for the UX UI person, is it shows that we don't have just a very simplistic way of saying, I'm going to show a form, I'm going to have them fill that out, they're going to hit a button, and that's just going to save it to a table, right? That's how most applications are built. What we're going to do instead is going to say that hitting this button sends a command that I can either accept or reject entirely. I can have a transaction there, and that's an important concept, not technically, but also from a business perspective, both sides, right? This is where we're marrying those two sides quite well. And what that drives from a UI perspective is a command-based UI, which is at the heart of what every designer wants in their web applications, is the ability to have componentized pieces that act with the system in a predictable way so that they can piece together what things are supposed to be behaving like and looking like. And that's a huge, let me just speed it up because I think, this slept, yeah. I don't know how far we're at 8:30. How much time do we have?
We have about 10 minutes.
10 minutes, okay. So the other side is inform. So the same diagram, but we're looking at the green box. That's a read model. And that's a projection of what we have stored in the system already on this ever-growing ledger of fact. We can use that for a number of different purposes. And one of the key things that separates this approach from how we've treated data before is that we're not afraid to make many of these. We can make a view that works for accounting. We can make a view that works for current online, shopping cart contents, whatever it is. We don't need to go to a single model. We can interpret the data as we like, and more importantly, as we learn more about our business, adapt those things as well. So there's a whole section on how we move this in an agile way forward as we discover more about our business and what we need to do. So create your own reality as long as it's based on facts. And we already agree that we already agreed how those facts are getting in there. Next things that we need to do is we need to understand. And that means we cannot have anything on the system that somebody doesn't understand in the organization. So whether you're a UI person, whether you're a CEO, whether you're a programmer, customer service rep, you must understand everything. And sometimes we understand them, but they're not really things that are useful. For example, we're working on an app for replacing Uber. And some of the external events we had to take in were coordinates, longitude, latitude. How do you think that would be for specifying whether you can pick someone up at an airport, right? That would be pretty crappy. You'd have to commit the coordinates of where the airport is and triangulate where, do all the calculations to see if the taxi's within distance to pick that person up. So the translation there was simply, as these different coordinates were coming in from a car driving, is you translate them: entered airport zone, exited airport zone, entered downtown zone, exited downtown zone. Now, those terms we can use within the business to specify the software, to specify the system itself. It doesn't matter that it's longitude and latitude. We can understand that, but we've adopted something better that we can understand. Integration is really just done by to-do lists. If I want to send an email to someone, I really have a robot there that's going to be looking at a batch job of where I have to send emails. And when that robot is doing each one, it's going to check them off as done. Of course, implementation may vary, and you obviously may do more reactive patterns to do that. But in order to communicate what's going on, leave it at that. It's a to-do list. It's getting done by something. And when it's done correctly or incorrectly, it gives the resultant event. And you store that as what got captured after that. And that feeds back to the way that diagram works. And I think I'll end it on that. There's a lot more to this. But I haven't seen a single collaborative document yield so much value to so many people from so many disciplines ever. So, any questions?
Can we get on the data?
Sorry?
Can we get on a review list?
Sure, yeah.
Question for you. When you showed commands and you talked about the transactional aspect, would you envision like a write-through transactional database managing that, or is that just kind of an arbitrary subsystem that handles the transaction, or are you envisioning that transactions are handled on the ledger itself?
It really doesn't matter. I see a lot of this as being 4 simple methods that you implement in any way you choose. Some of them you'll see as hydrate for getting state, and that's another way of doing a projection off of past events to get something like a read model that's specific for being able to handle the next command. There's the read models that handle an event, that give, as events come in, all those green boxes, they're live reports, essentially. So as new things happen, they get updated, and you have the current view that you want to see updated in real time as things are happening. There's 2 more, but it really goes down the rabbit hole of CKRS and event sourcing. There's publish and subscribe, and that's pretty much it. But it's about, if you're talking about handling the transaction and then storing it somewhere, it's really up to you. So I mean, that ledger of events at the bottom could be a one table in a database in Postgres that has 3 columns, one for indexing or something, but you're getting something that's ordered. And that's really important, because if you can't guarantee order, you can't rely on that as something that you can specify and predict how the system will work. So ordering is very important in that aspect. So does that sort of touch? Maybe you can repeat your question a little bit more specifically.
You talked about like booking a hotel room.
Yes.
Booking a hotel room, you're requiring some form of distributed consensus to say this particular individual gets this particular room while other individuals are trying to get out of that room. So you could do that by saying that little blue box represents the transactional database, and I try to make an update to that transactional database. If I'm successful, then I produce an event off the ledger. And that would be kind of front-loading the transactional burden into a more traditional mutable database. The other way would be to say, I'm going to put my claim to that room on the ledger. You're going to put your claim to that room on the ledger, but because my claim arrived there first, I get the room.
Yeah.
Now I'm doing the transactions on the ledger itself.
So that's, I mean, you can contrast 2 systems. One that's a little bit not as important to do as a ticketing system for concert tickets, right? I use that example. So you definitely have this reservation system where you have to really be explicit about when someone is online, when they say they're interested in something, they have a window within which that is locked, and you could have warmed up 10 servers that have specific allotments of tickets and all that. So that's where that business will probably be expanded on that diagram to be quite thorough in terms of what happens. In terms of something like a hotel booking, you can usually just go ahead and look at the previous events and say that is the count now 0 for availability of that type of room, then give it a synchronous error and exit and say, sorry, no more rooms. Otherwise, just put something else on the ledger. And how you do that is you have streams, for example, in Event Store, what James wrote. You're able to look at not just one giant long stream of events, but you can see finite small event streams that could be correlated with something like a room type for a particular season in a hotel. And then you can see the state of that particular inventory type in the hotel by just replaying or looking at, inspecting those events and seeing whether you're over or under, or if you're allowed. And the simple action is just store one saying, yes, if I was allowed to book a hotel, that particular inventory, then I do nothing else but put another event on that ledger that does that. The next person that comes in is going to get the error because it's just run out. That's what I would do. Now the implementation, maybe you can talk a little bit more to the same question from...
Yeah, so constant tickets is a much better example of this.
Yeah.
Actually, hotels don't do that.
Yeah.
So hotels overbook. They account for people who don't show up. They take into account like loyalty program membership when you check in. So it's not like there's like a finite reservation system. Like if you stay in a lot of hotels, it's not common to get warped. But if you don't, it is pretty common that they'll, people show up at a hotel and they'll say, actually, we don't have a room for you because we overbooked, and everybody showed up. Like we're going to take you to this hotel instead. Like reservations is one of those patterns where it's a whole domain model in and of itself.
Yeah. Same with flights, right?
Flights are
Yeah.
crazy.
Yeah, yeah.
There's a big movie about how flight works from IATA, who then subsequently got bought by Google, and it's worth reading because it's an NP hard problem. Like just to work out a price from like Austin to Seattle is literally an NP hard problem. And, like, out of interest, does anybody know? You know when you book a flight and you get the 6-letter code back, like the record locator. Does anybody know what that is? You must. No?
It's a slug?
Nope.
I forget what it is. I don't
It's a base 36, I guess, encoded memory address into a mainframe.
So yeah, the implementation's a detail. just show that diagram. Yeah, let's do 2 more questions, I guess.
Can I have,
Yeah,
no,
sure.
we can go to the pub for we do have some time.
Oh, okay. So we can do another 10 questions if they're short. If they're short.
So one of the things I was wondering is, do you have in mind, like with Alberto has this sort of workshop model. So do you have that in mind for event modeling too?
It's run exactly the same way.
It's run as a workshop.
It's run exactly the same way, except that the artifacts that you're producing is something that's a workable solution.
So that was my other question.
Yeah.
2 things is, so you're going to go to a workshop, so people are going to sit around, you're going to have people from all these different disciplines.
Mhm.
You're going to have different colored stickies that kind of match. Was that
Only 3 types of stickies, and then white paper for your, or not even anything. It could be just whiteboard drawings for your wireframes.
Okay.
That's it.
And so you get the commands and the events and the
Read models.
read models.
Yes.
And then transformations? Was it
No, those are just patterns of using those. But that's the interesting part, is that as we go on the bottom here, these are just,
It's the shorthand of saying like,
those are, that's using those particular components to specify them, right?
Those are the things that are.
Yeah.
Four things in the upper right.
Yeah.
Okay.
So a projection is just, a projection, for example, is a given when then, without the when, because there's no command. It's really just given these events, I expect my availability chart or calendar to look like this. And everyone can understand what that is. Yeah.
can you talk about the y-axis here? So you have two rows of UI. Does that represent 2 different applications?
Yeah, so there's a lot, as I said, I cut this talk short. Let's just work off of the complete diagram. Yeah, the fact that there's multiple rows of the orange means that you can organize subsystems. So that I can have my payment domain at the bottom, I could have my room inventory subsystem in the middle, and I can have my user authentication or whatever else I want in the third one. Yeah, but Yeah.
The lower UI length is web apps.
Yeah, it could be, yeah, exactly. It's about how do I organize all those facts so that it makes sense. And notice that I didn't throw in any specific words from domain-driven design or any other disciplines so that I don't lose any audience. So I can talk to the CEO, I can talk to non-technical people, UX people can talk to people that are not versed in journey mapping or other specific nomenclature from their expertise. You're using, these are information systems. They're really simple. You're moving information from left to right, maybe transforming it a little bit. You're not solving a computer science problem. You're not writing a new algorithm for encryption. You're really just organizing data. And so there is no reason to have special terminology for it. You should be able to communicate those things to everyone. Yes?
The Twitch audience has a question.
Mm-hmm.
Sponge Ruiner says, what's the best way to get started with event modeling?
Event modeling would be simply just to do it for there's a number of the book's not out yet, but there's a number of talks out there. So I would basically, you could use Alberto's book, but throw away all the stickies that are of different color than what you see up here, because it does work. The workshop is very similar in terms of how you run it. Things like a fuchsia note for important decisions. There's no reason to have some standard for it and complicate this anymore. You can put a little star or draw something on the whiteboard or do whatever you need to do. Maybe make a note. But what you want is to really have a unobscured picture of what the entire system is going to do from end to end. And so sometimes, when you have versioning with this system, like you want to change the design halfway through because you discovered some stuff, you simply change this and you can hold it up against the old version and see which slices you've introduced. That gives you your change management, the scope of it, how long it's going to take, how much it's going to cost, right? You have all of those predictable things that you expect, like you would if you were building a house and you had a blueprint. So you want that predictability, and I think we should all be striving to make this more of an engineering practice than just throwing things against the wall, as some of people have been doing. Yes?
I'm not sure if it's just your diagram, but I'm looking at the thing on the left, the UI that has a command that's got the orange event under it, and it doesn't seem to relate to the rest of the system. Is that?
Yeah, yes, it should probably somewhere be shown on a screen if it's important. So yeah, it's probably just an incomplete event. Interesting part about, this is kind of like a sample of what it looks like. So yes, generally that's a good question, because when you're doing this event, like you'd be saying, yeah, boss, we're doing this command. You said it's really important, but I don't see it being used anywhere else in the system. I can't draw a line for that email to anything else. Why are we asking for emails? We're kind of unnecessarily scaring people off, and we're not using that information in the system, right? In the end, we have to revisit that. So exactly, and that's one of the purposes of this diagram, is to be able to draw the lines all the way through the system as an example workflow to show where information goes. And so sometimes you might have, the thing that differentiates this from event storming as well is that you don't have any decision points. Everything is linear. So if you want to show 3 different cases of someone failing a login and retrying and then succeeding, someone adding too many things to their cart and then backing out, taking one out, and you put all of those different things in a row, or you do an alternate entire stream, but you want an example. And this goes back to the very beginning of my talk, which means taking advantage of the storytelling aspect of specifications and why it sits in people's heads better. The minute you start putting decision trees into diagrams, you lose understanding. It just becomes too much of a cognitive load to memorize a choose your own adventure book rather than memorizing, what a book was end to end, right? It plays better with our memories, and it's a better communication mechanism. So that's a active thing that I kind of noticed about what happens when we try different things, even like mind maps and other ways to really share information. Stories tend to be much better at communicating things. And so we definitely don't want to have anything like, oh, this could fail. Some of the streamlining in event storming is to have one major flow and show alternate flows down below. What we usually do is when we have one particular slice we want to show where that command might fail and what other scenarios are, we would have a whole bunch of given when thens underneath somewhere. Like even the real-time board, you could have this at the top. Who uses real-time board here? Everyone know what that is? It's like a real-time kind of canvas that's web-based. You can quickly share with people across the world, but it has a way to do sticky notes and color them, and to do wireframes. It has templates for wireframes as well, so you could have the mock-ups of all your screens. You can take a particular workflow, an entire workflow, copy it, put it down below, do a second one. You could do the given when thens below and draw lines to that you're explaining this one here, and everyone can look at it. What you're after, again, is something that's easily shareable across multiple disciplines within the company with as many people as possible, so you don't have to have the thousands of meetings during the project. Everyone knows what the business goals are, what the business vision is. Everyone knows what the technical strategy, what, you know, these things, these orange events are your transactional boundaries. They answer quite a lot of business and technical questions on what the vision is. So this erases 90% of the meetings that you would ordinarily have. We don't have any stand-ups. We don't have any retrospectives. We throw away 99% of the Agile book because it's just easier this way. Okay, I think one more, or we're done. Okay, good. Thanks.